things about the ACCESS-NRI model with a quarter-degree ocean. So, well, this is a bit of motivation. I'm not going into detail, but the idea to increase the ocean resolution is often atmosphere-ocean interaction is seen as the ocean is just kind of, it's only a one way, so from the atmosphere to the ocean, and the ocean is just kind of responding to more the large-scale atmospheric forcing and the small-scale variability in time and space. It's kind of just seen as noise. But there's been recently a bit more work that also highlights the role of the ocean to feed back to the atmosphere. And that's kind of this point down here. So especially for the mesoscale, when you imagine you have a large front in the ocean with warmer and colder temperatures, sea surface temperatures, that will have an effect on the atmosphere above and change the winds as well. And this last point on the temporal scale, there's been a study using the OM2, so the ocean-only model with different resolutions, and they looked at the upper ocean heat content and found this decadal variability that pops up if you include the mesoscale. And the suggestion of the paper is that that should have an effect on the atmosphere as well. So it's kind of the motivation why a higher resolution ocean is not only important to better simulate the ocean, but also the atmosphere. Yeah, here are just a few key points about the model. I guess you're mostly familiar with that. So the ocean is MOM 5 and sea ice is size 5. So these components are taken from the COSIMA, so the OM2 version. Yeah, the atmospheric model is the here model and then coupled to cable. And we currently have a simulation that's 500 years for present day. So the figures I'll be showing are from that simulation. So my take-home message is here. I put it at the beginning. I thought it's maybe then easier to read the slides of the figures. So basically, the main biases that exist in the 1 degree CMIP6 coupled model, they stay with the increased ocean resolution. We do see changes in those regions where the ocean mesoscale is important. So the western boundary currents, for example, so in the Southern Ocean, so regions where we have lots of eddies, there are regions where we see changes. Then in this quarter degree ocean version, that develops this multi-decadal variability, which is driven by occasional deep convection in the North Atlantic and the Labrador Sea. So I'll show you a bit about that. But I guess the point here is that when we have a quarter degree ocean, we can resolve the mesoscale in most of the ocean, but kind of in the mid latitudes or so, but not really in the high latitudes. So this problem of deep convection in the high latitudes is not solved, I guess, in a quarter degree ocean. So you need to go to higher resolutions. And then at the end, I'll talk a little bit about some developments. Okay, so I just picked a few random figures to first just show some of the biases. So here's sea surface temperature, and what I'm doing is I'm comparing the quarter degree coupled model here top left to the 1 degree coupled model, and also to the ocean only version where applicable. And at the bottom here we have the observations. So that's the full temperature field, and the other ones, the models, are the anomalies. So first you can see the biases are smaller in the ocean only version. I guess that's to expect it as it's forced by the or reanalysis product. But when you look at the coupled model, you can see that mostly the pattern of the biases, they stay the same. So that's kind of my first point. So the bias we have in the 1-degree coupled model is pretty much the same, the pattern at least, in the 1/4-degree model. For sea surface temperature, it's actually larger in the 1/4-degree, and especially here in the Southern Ocean, like in the Pacific sector, it's even warmer. So increasing ocean resolution doesn't fix, I guess, these biases. Similar for sea surface salinity. Again, the anomalies are much smaller for the ocean-only version. And then for the coupled model, the patterns are quite similar. And yeah, kind of the same issues with, for example, this fresh bias in the Pacific equatorial region here in on the eastern part, which is connected to El Nino. Yeah, so these patterns, they stay the same. Here's now the surface air temperature. So on the left, it's the field from the 1/4-degree ocean version, and then the bias is on the right, so you can see this warming in the Pacific sector and the Southern Ocean, which we also saw on the sea surface temperature, and it's also this air temperature. And mostly we have a red bias, so mostly it's warming when we increase the resolution of the ocean. Another example is the surface speed. So I don't have observations here, so I plotted on the top, bottom right, sorry, the 1-degree ocean-only version. And kind of when you compare those two, so on the left we have the coupled model, on the right we have the ocean-only version. When you go from the lower resolution to the higher resolution, you can see more of the details are captured. So especially in the Southern Ocean, there are lots of eddies, and then these western boundary currents. And that's similar in the coupled model. When you increase the resolution, we can capture more of these details. Overall, we have, when we go to high resolutions, we have more kinetic energy. So here in the middle, I give a few values. So we always have this jump of more than doubling the total kinetic energy, going from 1 degree to a 1/4 degree, and that's similar for both, where the coupled model has overall larger values though. I believe this is the last slide on kind of this point of the main biases. So here I picked the mixed layer depth. I guess this is just to show the problem of the high latitudes. So on the bottom right are the observations, and then the fields for the other models. So what I did here is so it's kind of it's not one season. I kind of picked always when there is the deepest mixed layer depth for a particular grid cell. So it's kind of winter in both hemispheres here. So the main issue that we have with the models is, so if you look at the observations on the bottom right, you can see that, oops, deep mixed layers in the Southern Ocean, and then on the near the continental shelf, and then in the Northern Hemisphere, mostly in the North Atlantic, in the Labrador Sea, and here the Northern Seas. But then when we go to the models, they have 2 deep mixed layers, although this might also depend on the definition. So it's very sensitive to definition of your mixed layer depth, and there might be a different definition of the observations. And there's, like, depending on which observational product you use, there's also quite large variability. But mostly you see in the Southern Hemisphere these open ocean convection regions in the Weddell Sea and the Ross Sea, and they are in the 1/4 degree as well. We know from the 10th degree ocean only version that for that particular model, then they disappear and they are on the continental shelf. So that's how we observe it in the real ocean as well. But the 1/4 degree is not enough resolution, and there might be other factors as well, to simulate the deep convection correctly in the high latitudes. One last point is for the Labrador Sea. So this deep convection that we have in the observations and also in the ocean only version, that's missing in the coupled models. Well, this is where this multi-decadal variability comes from that I'll talk about in a bit. But yeah, that's an issue that coarse resolution models have, and these ones have it as well. So 1/4 degree is not enough. Okay, so here are just a few figures that show the difference when you kind of increase the resolution in particular regions where eddies are important. And with the 1/4 degree, unless we go to the high latitudes, we mostly resolve or can resolve eddies. So what I'm showing here is sea level anomaly, the standard deviation. So the observations are here on the bottom right again. And this is kind of as a proxy for variability in surface speed. And if you, for example, first look at the 1 degree coupled model, you see like the southern ocean is mostly just blue. So yeah, underestimates that variability a lot, and also the western boundary currents. But then when you go to the 1/4 degree, it's actually much better. And the coupled model also performs better than the ocean only model. So I guess in that regard, the 1/4 degree coupled model actually does a pretty good job. And yeah, it's nice to see that these regions where we expect more variability, they pop out in the coupled model. Here I'm showing evaporation, so just a different field. Again, on the left, the coupled model, on the right, the ocean only model. And on the bottom is the full field from the 1 degree, and then on the top is the anomaly between the 1/4 and the 1 degree. So yeah, here I just want to highlight again these regions where, excuse me, we have large eddy activity. These are the regions where we see the strongest changes in the evaporation field. So basically we have now stronger gradients in the surface, in the temperature fields, in the winds, and then that's reflected in the evaporation. And yeah, so this is surface air temperature again. So earlier I just showed, like, talked about the main biases with the Southern Ocean here. But if you again look at these regions like Agulhas current down here and western boundary currents, you again can see these shift kind of there when we go to the higher resolution. Okay, so then I'm moving on to this multi-decadal variability. So what I mean by that is, for example, if you plot here at the very top in this dark blue, the sea surface temperature, the global sea surface temperature, you can see once there's like an overall increase, spin up, then there's lots of small scale variability, but there's also in this dashed blue line this multi-decadal variability. And that's not present in the 1 degree, that's in the light blue, and also not in the ocean only versions. So in the middle panel, I show the PCs of an EOF of upper ocean heat content, but would be similar for sea surface temperature. And the light green shows the spin up, and that's mostly driven by the Southern Ocean. But then this darker green for the second EOF that picks up this multi-decadal variability. And this variability is not just in the upper part of the ocean, but for example, at the bottom, I'm showing time series of the AMOC, and in the dark green, it's at 26 north. So you can see the strong variability in there as well. And that's matching pretty well in the dark blues against the surface temperature, the same frequency. And then the lighter blue is the AMOC just further south in the southern hemisphere, 30 south, which has the same pattern, just shifted a little bit by a few years to later. So I guess that makes sense because the source of this variability is from the northern Atlantic. So what happens is that in some or most years, we don't have convection in the Labrador Sea, but in some years we do. And this makes this huge difference. So what I'm showing here are composite plots of either positive or negative phases of this variability. So on the right is this, what I call a negative composite. And that's kind of the state that you saw in plots that I showed earlier. So for the whole, like a longer time mean. So what I show here is sea surface temperature. And then this dark blue line is the sea ice edge. And at the bottom, mixed layer depth. So very shallow or no deep mixed layers in the Labrador Sea because it's covered by sea ice. But then some years where I have this positive composite on the left, the Labrador Sea is actually ice-free. So this sea ice edge is now further into the Labrador Sea. This means the ocean surface can warm, but we also have then deep convection. And this affects the AMOC then as well. So that's why we can see it in the AMOC as well, and not just at surface. So this variability, I guess, is not what we observe. So it's just like because we only have in some years the deep convection, not in all years. It's only popping up in the quarter-degree ocean, so maybe because then in some years, I guess, at least we get the deep convection. And this issue is not unique to the ACCESS model. I didn't put other references here, but there are other models that also see this variability. And yeah, I guess it's quite difficult to simulate this region. And it's very sensitive to how much fresh water is exported from the Arctic. How is your sea ice coverage, and how good or bad does the model do with convection? Okay, so then are just a few points for my future plans, at least, with the coupled model. So we want to fix a few things with a quarter-degree version. There's an updated bathymetry product. There were some issues around Antarctica and the Southern Hemisphere. We also want to change a few of the interpolation weights between the atmosphere and the ocean. So when they talk to each other, because for some fields, you could kind of see the imprint of the coarser resolution atmospheric grid onto the higher resolution ocean grid. And we probably run a whole new simulation, so start from 0 again and do not continue. And maybe this multi-decadal variability disappears and might stay, but yeah, I don't think we are trying further to get rid of this variability. It's, I guess, just a feature of the model. So if you do any analysis, kind of be aware of this, and you might have to remove that signal depending on what you want to look at. I'm also interested in setting up a coupled model with the Chancery ocean, and the main motivation is that hopefully we can then do a better job in the high latitudes. So yeah, what did I put in? Yeah, so denser fault formation in the Antarctic, so that it's on the continental shelf. So that's when you, if you remember, I showed these plots of the mixed layer depth, where we had these large areas of open ocean convection in the southern hemisphere. So maybe, yeah, it's not just dependent on the resolution, but maybe that will help. And then I guess it will also change the deep convection or North Atlantic deep water formation in the North Atlantic. Yeah, and there are also some people here at NU interested in, if Dave would be here, he could talk more about this, and maybe running paleo simulations on with a very high resolution. So some tests we are doing at the moment is using the high resolution ocean only model and force it with some atmospheric output from the coupled model to see how good or bad the deep water formation is. And yeah, it's promising so far, but yeah, we shall see. It's kind of future plans. Yeah, so that is for me. Any questions? Siobhan?
Okay, got a few questions. Obviously, I mean, we obviously talked before about the Labrador Sea stuff, and I obviously picked up the Labrador Sea stuff in relation to the ice. One thing I find interesting in that those two positive patterns that you did, the EOF patterns, is you have the Labrador Sea pattern, both the Labrador and Greenland Sea on in that EOF pattern, positive composite together, while what's I've seen, certainly when I was talking a long time ago now, some of the observationists from the observationist and modelers from the, I think it's from UEA, they said they actually sort of oscillated between the two, the convection patterns oscillated between the two regions, and that would be something you'd have to check in the literature. But and they were looking to see whether it happened in our model.
In these two regions.
Yeah, and they also wanted to see whether the Weddell and Ross Sea oscillated a little bit, and that was ages and ages ago. But I guess it would be something that we might see if we did eventually get to a high resolution model when we got things better. I think they looked for it in Ockham, which was again what was being the model they were using in the UK, and again that would have been a force model rather than a coupled model. But again, it would be something that possibly the North Atlantic NEMO type people would be also looking at in their models. So that would be the issue. I mean, yes, obviously Labrador Sea convection is just very intermittent. And one question was how long was your time? Was when you, because the first plots on mixed layer depth, you didn't actually have any in it, which was interesting, because how long was that? How long was that? Was that a 50-year average you had in?
I used a 100-year average. So
that was a 100-year average, and it showed nothing, which was interesting.
Yes, and that average, it showed nothing, but I think it depends on,
yeah, because it's so intermittent.
Average you use.
Yeah, because
so if I would go to like the last 150 years, then you have this.
Yeah, you have it maintained. Yeah, because we started seeing it about year 60, and I saw the year 120, and it's interesting. It may have calmed down. The other thing that we're starting to look again at now is CQ881, and you did a little bit of analysis probably before you went overseas on that, and the mixed layer depths are different in that one. This is the one with the change neutral physics in, and they're much shallower. So I know you haven't been as happy with that one because it's still got the multi-decadal variability, and but both of the Weddell Sea variability mixed layer depths in certainly the documentation that Martin shared with us are less shallow. We've been mostly Arnold's mostly been looking in the tropics in it, but noticing that those mixed layer depths are shallow, I was going to start looking at the polynyas in that, because the polynyas were an issue in that Weddell Sea run in that run. So I thought it might be worth, even though I understand you don't want to follow up on that changed neutral physics one, it still might be worth looking a little bit at that convection properties more, because the mixed layer depths are shallow in it. But I certainly think going to the 10th degree is the next step. The question is, you do want to, apparently you want to run it with the N96 atmosphere, which I'm a little bit worried about, because the scales involved, you've brought out atmosphere weights to the ocean weights. That's quite a big, strong difference in scales. So that may be a thing to consider, whether that's going to be the right mix. But yeah,
it's true. It's so yeah, my idea is to just keep the super coarse atmospheric resolution, and then just have this very high ocean resolution, which might not work. But I guess I'm having hope. There's a group in Germany, and they have it's a global model, but then a Southern Ocean nest with a higher, with the high resolution, also 10th degree ocean, and still coarse atmospheric resolution. And for them, it seems to work pretty well. So I guess that's where I take my hope from.
Yeah, I guess the RV model, which has finite elements, that they have very different resolutions in the atmosphere compared to what they have very high resolutions in the ocean as well.
That's a different model again.
They've managed to manage that way as well. But certainly the Met Office, you found they had to increase resolution in the atmosphere when they went to very high resolution in the ocean. Yeah,
and on that other point with so for the rest of the group, we did one experiment or one test run where we changed some of the parameters for mixing in the ocean. And in that run, we kind of reduced the convection. So we kind of, in the ocean only, we then start to see a similar variability, but kind of, I guess, flipped. So I don't know if that's what we want. Like, we do want convection in the Labrador Sea. It's just not regularly. It's just a few years here and there. And
is that CQ880?
Don't have the convection.
Is that the CQ880 one you're thinking of?
Yeah.
Okay. Well, we haven't really looked at that one yet, but I intend to have a look at that in relation to what's happening with the convection in the ice, and also the convection in the ice in the Weddell Sea, because what was happening previously, both the Ross Sea and the Weddell Sea were opening up into open ocean polynyas all the time, and that really isn't what we want either. So there's issues to look at there as well. So they're not ideal ones yet for using for awful climate potential CMIP7 simulations.
Gabriel.
Okay, hello everyone. Thank you very much for your talk, and good job on setting up this new model configuration. I just have basically, I think, 3 quick questions. The first one is, at the very beginning of the talk, you said that you have set up a present day configuration for this control run. And what exactly do you mean? For example, what was the CO2 concentration for this run? And when you were comparing with the 1 degree coupled model simulation, are you comparing with pre-industrial, or is it any other run? And just you can just go for those 2, and then I ask the last one.
Okay, so I should clarify that Martin Dix mostly set up this model. So I'm just looking at the output. I'm not too sure which years exactly the present day is. Maybe others in this group might know. I think it's just whatever the standard is for the CMIP experiments. And I used also then present day for the 1 degree.
Great.
It's like 1980, around 1980, something, or 2000, yeah. It's from Martin's wrong. Yeah, both your 1 degree and course degree or the present day wrong.
Yeah. Okay. Thank you very much, Arno. And would you know what are the costs for running this model? Like, for example, how many SU it takes for each year and how long it is.
Yeah, I
missed
must
this.
know this, but I had some numbers here.
Yeah.
So here's some numbers about the performance. So in black is the 1/4 degree coupled model, and then the gray is the 1 degree, the CMIP6.
Perfect. Thank you very much.
Dietmar was the next one I noticed.
Yeah, interesting run. Obviously, the biggest one you have missed is the tropics. So I would wonder what the ENSO does. Although I don't have time to look into it, but are you having any plans to look at ENSO?
I'm not an ENSO expert.
No good.
I didn't
No
do
good.
much. I didn't come last time.
Okay, but I think it would be worse if somebody looks into this, maybe Arnold or so.
Yeah.
But
So I didn't know how much
main,
Arnold talked about it, so I just skipped it over here.
Yeah.
But
my other question, so my other point is, so you increased the ocean resolution, and more or less, I think you said the biases are about equally bad. And a few years ago, we did the opposite. We reduced the atmospheric resolution, and we find that the biases are also equally bad. So I would argue, which I have been arguing for 20 years, that resolution doesn't matter. The biases are in the models, and it is the processes that we need to improve in the models, right? Because since I have an N48 model that is about equally good as your N96 with a 1/4 residual ocean model, I think it kind of suggests that there are fundamental problems that might actually be solvable in a coarse resolution model. Not necessarily your Labrador Sea convection, but the tropics on the large scale, I think, are not necessarily, the problem is not in these kind of things. So therefore, I think these kind of experiments are really interesting. And if we see biases that appear in all resolutions, it might be a strategy for us to use the coarsest resolution possible in trying to fix things on a coarsest resolution. And then hopefully this propagates then to higher resolution to make it even better. Right?
Yeah, it's a good point. Yeah, I don't know how much, like if the resolution doesn't change, maybe coupling time stepping, if that.
No, I think this is all misleading. I think these
kind of going that direction, but
most of these problems are simply fundamental in microphysics of clouds and precipitation and unresolved problems like small scale convections that you will never really resolve. So I'm pretty sure that a lot of these problems are fundamental, cannot be solved by resolution alone. Resolution, certainly, if you increase it, it will not get worse. It will get better a little bit, but not as much as you hope for. So.
Yeah, good point. Thank you.